Please have your notebook out and be prepared to take beautiful, organized notes today. To try and help in your organization, I color-coded the slides to help signify when the warm-up was, when you had formal definitions, and then the slide for examples. Alright, let's go. Alright, and now's the time to review our parent graph transformations. So we're going to say that G is a general transformation equation for any parent graph f. So f could be a parabola, it could be a cubic function, an absolute value, it could be sine or cosine. F is any type of parent function, and then G is a transformation. So G has a, b, h, and k that will move that parent function around or make changes to it. So I want to describe or remind you what all these different variables will do to the parent graph. So this A right here is a vertical transformation. So this will cause vertical transformations like a stretch, and it will be a vertical stretch if A is greater than 1, or it could be a compression if A is between 0 and 1. So if A is big, it will make the graph stretch up. If A is small, it will compress it down. And then it can also reflect over the x-axis. So that's a vertical reflection if A is less than 0. B is very similar to A, but you see that B is being multiplied inside the argument. So everything inside of those parentheses, inside the argument, is a horizontal transformation, while everything outside of it, like A and K, is vertical. So B basically does everything that A does, except it's horizontal. So this is horizontal, stretch, compression, and reflection. Except the rules are a little different. So inside of the argument is kind of like the upside down, where everything that you think happens is the opposite. So if B will stretch, if B is between 0 and 1, B will cause a compression if B is greater than 1. However, this one's the same, so it will reflect over the y-axis if B is negative. Oops, if B is less than 0, which will make it B negative. Okay. H and K are my shifts. Because H is inside of the argument, this is a horizontal shift. And the horizontal shift will go left if H is less than 0, and right if H is greater than 0. Okay, which makes it kind of opposite. So if H is less than 0, if H is negative 5, that will be x minus negative 5, which is x plus 5, which will still go to the left. So x plus 5 in the argument goes to the left because we have this negative sign right there. It makes things do the opposite. Okay, and then finally we have our vertical shift. And this will go up when K is greater than 0 and down when K is less than 0. That makes sense. So that's just a little review of the different parts of an equation that will cause changes to a graph. On this page, this is just a library of different graphs. This is only if you want it. So if you're someone who's like, I know what a parabola looks like, I know what a cubic looks like, I know what an absolute value and a square root looks like, if you know those things, cool, you're good. You don't need to write this down. However, if you're looking at these and you're like, ooh, I didn't know that this equation would make this graph. What? If you're looking at that and you're uncertain, you should definitely copy down this library of graphs. Or if you forgot the difference between sine and cosine, you should maybe copy down this library of graphs. It'll just come in handy for you to be able to recognize an equation and know, hey, I know that that equation looks like that. I'm good. Okay. So let's do an example on transformations. We're given a function k, and k already has lots of transformations. So it has the 2 in the front, which causes a vertical stretch. Then the x minus 3 will make the absolute value shift 3 to the right. And then the plus 1 outside of the argument causes the graph to go up by 1. Okay, but I want to make, the point of this problem is to make a change to k of x to elicit the following changes. So in part A, it wants me to make k point down. So if k was an absolute value, that goes up. Now we want it to point down. Like that. So what kind of transformation makes graphs point down or reflects like that? That will be the a value. I need to make my a value negative. So one change I could make to k is just put the negative sign right out front like that. And then the graph will point down. Cool. B, shift k further to the right. So the x minus 3 was already going 3 to the right. So that means I just need to go farther. I need to make that h value even bigger. So I just need to choose a number bigger than 3. What number do you think I should do? 8? Okay. Good choice. There. So if I made that 8, then my graph k is going 8 to the right. Cool. Part C wants me to vertically compress k. Okay, so I need to vertically compress k. That means I need to make my a value very small. So my k value was 2. I need to make it less than 1. So maybe I'll make it 0.02. Keep everything else the same. That will compress it. Then finally D, shift the vertex below the x-axis. So right now that plus 1 has the absolute value shifted up 1. So I want to shift the vertex below the x-axis, which just means I need to make the k value negative. So my k value needs to be negative. Everything else can stay the same. Negative, what'd you say? Negative 3? Okay, cool. It has that double negative 3 look then. So that will shift the vertex down. So if you want to check any of these to see like what does this really do to the graph, go ahead and go to Desmos and just type these equations in and you can see how the graph is transformed in each of these iterations. Sometimes it's nice to graph all of them at once, since all of them just have like one tiny change, so they will look very similar, but you can see what the different values of a, h, and k do to the graph. The final topic we will be reviewing today in our functions review is domain restriction, which is a new vocabulary word for you. I know that you all know what the domain is. The domain is all the possible inputs for a function. And I know that if I were to give you a graph, you'd be able to look at the graph and determine what the domain of the function is. However, domain restrictions are when you're able to look at an equation and know all the values for which the function is undefined just based on the equation. And this is a really important skill because you're not always going to have a graph and you're not always going to know what the function looks like. But you will want to know what is the domain of this function, for which values of x is this function defined. And so when we're finding domains analytically from an equation, there are 3 rules that you need to memorize in order to know what are the values for which this function is undefined. The first rule is that you're not allowed to divide by 0. Okay, dividing by 0, that's not allowed. And so the types of functions this is going to affect are reciprocal functions. So rule number 1 affects reciprocal functions. Okay, and we know reciprocal functions look like 1 over x. So in that case, I know that x cannot equal 0. That is the restriction, the domain restriction that I'm putting on the function. If the function is 1 over x, I know x cannot equal 0. And it's really similar if I were to make this slightly more complicated, like 7 minus x. Then I know that 7 minus x cannot equal 0, so x cannot equal 7. So x does not equal 7 would be the domain restriction there. Alright. Second rule, taking even roots of negative numbers. So if you have a square root, you know that you're not allowed to take the square root of -4, for instance. The square root of -4 is an imaginary number. It's not a real number. And so that is not in the domain that we want to include. So for number 2, this means even roots. So an even root would just be like the square root or the 4th root, right? Or the 6th root. You get the picture, any even root. And so if I have the square root of x, if I can't take the square root of a negative number, that means that my x value has to be greater than or equal to 0. So this would be my domain restriction. X is greater than or equal to 0. If I had something a little bit more complicated, like the square root of 1/2 x plus 3, then I know that 1/2 x plus 3 has to be greater than or equal to 0. If I were to simplify this and solve for x, then I know that x is greater than or equal to -6, and that would be my domain restriction. Okay, and then the third rule, a little less common than the first two, but you cannot take logarithms of non-positive number. So this vocabulary word, non-positive, a non-positive number is any negative number and also 0. 0 is neither positive nor negative, so a non-positive means a negative number or 0. So that means this affects my logs, obviously, and my natural log, my ln. So that means that if I have ln of x, or any log of x, that x has to be greater than 0. It cannot equal 0, it just has to be bigger than 0. And again, if I had something slightly more complicated in there, maybe I'll do a log this time. So log of, I don't know, x minus 12. That means that x minus 12 has to be greater than 0, so x is greater than 12. These are very basic examples of domain restrictions and how you can figure out the domain based on the equation. For most other function, the domain will just be all real numbers, negative infinity to infinity. These are the functions that you should memorize, because then you know, oh, if I have a reciprocal, a root, or a log, then I have to figure out what the domain is. Otherwise, the domain is just negative infinity to infinity. The only other, there's one other case if you have a piecewise function. So piecewise functions, you might need to check on that if they don't meet up in the middle. Okay, so let's look at some slightly more challenging examples, but not really, I feel like you got this. So determine the domain restrictions for the following functions. I see that I have an ln, so I need you to try not to look at your notes and think, all right, what numbers are not allowed to be in a log? Okay, so inside the argument, remember you need only positive numbers, can only have positive numbers in there. Okay? So that means that x minus 3 has to be greater than 0. So the domain restriction for this function is that x is greater than 3. For a reciprocal function, remember the denominator cannot equal 0, so can't divide by 0. So that means x plus 2 cannot equal 0, which means x cannot be negative 2. That is my domain restriction. So it's all real numbers except x cannot equal negative 2. Finally, a square root. Square root, you can't have negative numbers. So no negatives. No negative numbers. So what's inside of there? 2x plus 1 has to be greater than 0. I made a tiny mistake there. Can you tell what I need to add to my equation? It can be equal to 0. So square roots, you can take the square root of 0. That's no problem. So in this one, it can be equal to 0. If I solve this out, I'll subtract by 1. Then divide by 2. So x is greater than or equal to negative 1/2. Those are my domain restrictions. And this is it for your function review. So it's important for you to first of all have that library of functions that you know, so you're able to look at an equation and have a general idea of what it looks like. Know what values will transform a function, so what numbers will make a function stretch, what will make it shift, what will make it reflect, and then having an idea of what the function's domain will be based on these 3 rules for domain restrictions.